Hello, everybody. Final talk of Nicoletta on SKT metrics is on the way.
Okay, thank you. So, yeah, in this last lecture, I would like to discuss the relations that we can have between strong Kähler with torsion matrix and some curvature properties for the bismuth connection. So, in fact, today I will talk about bismuth-Kähler-like Hermitian matrix. So first, let me recall what we said in the first lecture of this mini course. So we said that if we have M, J, G, omega Hermitian manifold, which means M is a smooth manifold, J is a complex structure, G is an Hermitian metric, and omega is the fundamental form. Then in the first lecture, we said that there exists a unique Hermitian connection that I denoted with nabla B that has these two, so Hermitian connection, so means that nabla preserves the complex structure, so J is parallel, and also the metric. So also the metric is parallel, okay? So this connection is preserving the whole Hermitian structure, not just the complex structure or just the metric, okay? So there exists a unique Hermitian connection whose torsion, so let's say TB of X, Y, Z, so G is given by the torsion TB on X, Y, and Z, so X, Y, Z are, of course, vector fields. So this torsion is a three-form, so is a differential three-form. So the torsion is totally skew symmetric. Okay, so we said there exists a unique Hermitian connection whose torsion is a three-form, and in fact, we said that this torsion coincides exactly with dc of omega, where dc was minus j minus 1 dj. Okay, and we call this torsion bismuth, this connection bismuth connection. So such connection is called bismuth connection. Sometimes in the literature, it's also called Strominger connection, okay? So in some papers, you can find also this name. Okay, so in particular, we said that, moreover, we said that a metric omega is SKT if and only if, by definition, the torsion of the bismuth connection is closed. Because this is exactly saying that D, but the torsion is dc of omega, ddc of omega is 0. Okay, so this was the definition of strong Kähler with torsion metric. Okay, so also just for notation or remark, just let me recall the definition of the curvature tensor of a connection. So we will denote RB of X, Y, Z as nabla B of X, nabla B, Y, Z minus nabla Y, nabla X, Z minus nabla of the bracket of X, Y, Z, and RB of X, Y, Z, U. So with 4 entries, we have G of RB of X, Y, Z, defined as above, comma, U. So these are the curvature tensors of type 1, 3 and 0, 4, respectively. Okay, so these are the definitions of our curvature tensors. For the bismuth connection, these are standard definitions. And just let me first recall another fact that we said that nabla B equals the Levi-Civita connection. So this bismuth connection coincides with the Levi-Civita connection. So this is the Levi-Civita connection. If and only if the metric omega is scalar. And also, in fact, the bismuth connection coincides with the Chern connection. So this is the Chern connection. If and only if omega is scalar again. Okay, so if we work in non-Kähler geometry, all these connections are different connections, okay? So as you can expect, they will behave differently, okay? They will have a different behavior. So in general, the bismuth connection, so let's say remark, in general, the bismuth connection does not satisfy the Bianchi identity. That is, for instance, satisfied by the Levi-Civita connection, okay? So if you take the Levi-Civita connection, it does satisfy the Bianchi identity, but the bismuth connection doesn't. In fact, what we have, it's a formula by Ivanov and Papadopoulos. The following formula is due to Ivanov and Papadopoulos. Sorry. Okay. So if you consider the cyclic sum over x, y, z of Rb of x, y, z, u, so this denotes the cyclic sum, okay? Cyclic sum over x, y, z. Okay, for the Levi-Civita connection, this is 0. That will be the Bianchi identity, okay? But for the bismuth connection, this is not 0. And in fact, it's equal to the differential of the torsion of the bismuth connection, so x, y, z, u, plus nabla u of the torsion applied to x, y, z, minus this cyclic sum over x, y, z of g, torsion on x, y, torsion on z, u. Of course, this is for every x, y, z, u vector fields. So you see, first of all, we don't have the Bianchi identity. Moreover, you can see that the Bianchi identity is related to the differential of the torsion. And here, just let me point out that the differential of the torsion here, why it's not working? Okay, again, I have problem with the pen sometimes. I don't know why. Anyway, so the differential of the torsion is 0 if and only if the metric is SKT. Okay, so for instance, this term vanishes when the metric is strong Kähler with torsion. Okay, so let me just 1 second close this again, and let me share the screen again. Let's see if the pen works. Okay. Okay, so this is related to the differential of the torsion, we said, which is 0 if the metric is SKT. And also, you see that we have another element here that is related to the fact that the torsion of the bismuth connection is parallel or not. If the torsion of the bismuth connection is parallel, then these terms again vanishes. Okay, this is just an observation that will be, useful later. Moreover, nabla B does not satisfy the following condition. so does not satisfy the following condition. That is the following. So RB, if you compute, so the curvature for Jx, Jy, Z, let's say W, then this is not in general equal to RB of X, Y, Z, W. So essentially it's not of type 1, in the first two entries, okay? Because I'm saying that the bismuth connection does not satisfy this equality in general. And for instance, this equality is satisfied by the Chern connection, okay? So, but the bismuth connection does not coincide with those connections. So in general, doesn't have this Bianchi identity and these other conditions. So somehow this was the motivation for the following definition. So let me write the definition here. Let's say that for the bismuth connection, this definition was given by Angella, Otal, Ugarte, Villacampa in 2022. But in fact, their definition is inspired by a previous definition of Yang and Zhang in 2018. So what is the definition of Kähler-like? So the bismuth connection nabla B is called Kähler-like if it satisfies the following two conditions. First, we have the first Bianchi identity. Which means that if you take the cyclic sum over X, Y, Z of RB of X, Y, Z, this is 0. This is 0 for every X, Y, Z vector fields, okay? And second, if it satisfies, let me call this the type condition, okay? Which means that RB of X, Y, Z, W is equal to RB of JX, JY, Z, W for every X, Y, Z, W. Okay, so we will say that the bismuth connection is Kähler-like if we have these two conditions, the first Bianchi identity and this other type condition. Why the name Kähler-like? Because in the Kähler case, we said the bismuth connection coincides with both the Levi-Civita connection and the Chern connection. So in the Kähler case, the bismuth connection does satisfy these two conditions, okay? So that's why we have this name Kähler-like, okay? Because we are saying that the bismuth connection is behaving in a Kähler way. And of course, the metric itself, so the metric say G is called, or omega if you want, is called bismuth Kähler-like if nabla B is Kähler-like. So if the connection that is unique is Kähler-like. Okay, just a few remarks. So first, the Kähler-like definition was originally given, has been initially given for the Levi-Civita connection and the Chern connection. Because for the Levi-Civita connection, the second condition in this definition is not satisfied in general. And in the Chern case, the first condition is not satisfied in general. So actually this definition was originally given for the Levi-Civita connection and the Chern connection. So this Kähler-like condition. And it was done by Yang and Zhang. Yang, Zhang. In particular, they proved that if G is, let me say, nabla LC, so for the Levi-Civita connections is scalar-like, or if it is nabla-Chern Kähler-like. So I'm saying that the Kähler-like definition, I'm saying that these two connections are Kähler-like according to the previous definition. So if the metric is either Levi-Civita Kähler-like or Chern Kähler-like, then the metric G is balanced. So we talked about balanced metrics in the second lecture. So this was the definition. So the n-1 power of omega is closed. Okay. So they prove that if we have this scalar-like condition for the Chern or the Levi-Civita connection, then the metric has to be balanced. In particular, if n is equal to, so if we are on a surface, G is scalar. Because if n is equal to, the balance condition is just the Kähler condition. Okay. And moreover, so what happens? So this is some let's say history about this definition of Kähler-like condition. First, it was given for the Levi-Civita connection and the Chern connection. Then Angela, Otal, Ugarte, Villacampa, that are the ones that gave this definition for the bismuth connection. Actually, they gave the Kähler-like condition. So let's say this Kähler-like definition, let me say the Kähler-like definition for all the Goduchon connections. That we mentioned in the first lecture. So when you have a canonical Hermitian connection, so Goduchon proved, let's say, that the canonical Hermitian connection are prescribed by their torsion, and what we have is let's say, a line of connection parameterized by this T in R. Okay, we have a whole line of connection, and in this line we have the bismuth connection and the Chern connection. So they gave, so Angelo Tarugarte Villacampa gave this scalar-like definition for all these connections. And in fact, very recently, La Fuente and Stanfield proved that for a compact Hermitian manifold, if nabla T is scalar-like, with nabla T different from either the Chern connection or the bismuth connection, then the metric G is scalar. So somehow it seems that imposing some, let's say, Kähler-like symmetries for the curvature, actually it's forcing the metric to behave in a very particular way. For instance, it seems that, this theorem is saying that if you take one of the Goduchon connection that is not Chern connection or bismuth connection, and if it is Kähler-like, then the metric has to be Kähler. And in the Chern case, Yang and Zhang proved that if the Chern connection is Kähler-like, then the metric is balanced. Okay, it's not Kähler in general, but still it's balanced. So what about the bismuth connection? Okay, so this is what we are going to say. Okay, so yeah. So let me just do this remark that bismuth Kähler-like manifolds exist, first of all. So we are going to see an example, actually more than one. Bismuth Kähler-like manifolds exist, for instance, with an affino we gave characterizations for their existence on almost a billion Lie groups. Okay, we're almost a billion. Let me just recall, that means that if G is the Lie group, it means that the Lie algebra G has a codimension 1, a billion ideal. So we have some characterization actually under some additional hypotheses, okay? Under some additional hypothesis. And then later, Zhao and Zhang gave characterizations on nil manifolds. Okay. But I'm not going to talk about these results. So let me just give you an explicit example, okay, of a Bismuth-Kähler-like manifold. So, okay, let's take G to be the following. So G will be an almost a billion Lie algebra of dimension 6 with the following Lie brackets, okay, with the following structure equation. Okay, so we have, the bracket of E6, E1 is equal to E2, and the commutator of E6, E4 gives E5, and then E6, E5 gives minus E4. So these are the only non-trivial brackets, okay? I'm saying that the basis is given by EI, I from 1 to 6, okay? So this is almost a billion, you see, because we have this element E6 that is the only one that has non-trivial brackets, okay, with the other elements. So the codimension one, let's say U, generated by E1, E2, and so on up to E5, is a codimension 1, a billion ideal in G. Right? Because if you take any Lie brackets among these elements, they are all 0. Okay, so this is a billion and has dimension 5 in G. Okay, and then denote with G the connected, simply connected Lie group. So connected, simply connected Lie group such that the Lie algebra of G is exactly the Lie algebra we just introduced. And it can be shown that G admits a lattice. Okay, G is solvable. I mean, it's almost a billion, so G is solvable. Okay, so in general, we said that it's not so easy to understand whether when a solvable Lie group admits a lattice. But in some cases, we can find lattices. In particular, we can find lattices when we know that the Lie group is almost a billion. I mean, we have a criterion to understand when a solvable almost a billion Lie group has a lattice. So it can be shown that this group admits a lattice, and this is due, I mean, we have to apply a result of Bock. That I know it was this was mentioned. So this result of Bock was mentioned in Marco's lecture. Okay, so one can show that this Lie group has a lattice. So in particular, so let me call this lattice gamma, which means that M defined as the quotient of G over gamma is a solved manifold. Okay. So starting from this Lie algebra, we have an associated solved manifold. Okay, so let me I want to show that this Sol manifold has a Bismuth-Kähler-like matrix, an invariant Bismuth-Kähler-like matrix. So let me define J on G. So I will work at the level of the Lie algebra because everything will be invariant, and so it will be induced on the Sol manifold, okay? So we define J in this way. So J of E1 is equal to E6. And so since J of J squared has to be minus the identity, J of E6 will be minus E1. J of E2 equal to E3, and then J E4 equal to E5. Okay, and so in particular, J of E3 has to be minus E2, J of E5 has to be minus E4. Okay, so you can check as an exercise that J is integrable. So it's not just an almost complex structure, it's actually a genuine complex structure on the manifold. Denote so let me say, consider as G the metric such that this basis is orthonormal. Okay. So we fix this metric and we want to show that this metric is Bismuth-Kähler-like. So there is a general formula for the Bismuth connection says that we showed this formula the first day. The Bismuth connection is related to the Levi-Civita connection by this formula. Okay, they are related by this formula. So in particular, one can show using the formula, the Koszul formula for the Levi-Civita connection, one can show that for the Bismuth connection, we have this formula here. So 2 times G of nabla XYZ is equal to G of the bracket of XY minus the bracket of JX, JY, Z minus G of bracket of X, Z minus the bracket of JX, JZ, comma Y minus G of Y, Z plus here, plus JY, JZ, X. So there is this formula that holds on Lie algebras for the Bismuth connection. So what does it mean? It means that you can compute the Bismuth connection explicitly on the Lie algebra using, using the basis. Okay, so one can check that the only elements that are not trivial for the Bismuth connection are nabla B E2 E1 equal to E6, nabla B of E6 E2 equal minus E1, nabla B E2 E6 equals minus E1, nabla B E6 E4 equals E5, and finally nabla B of E6 E5 equals minus E4. So using that formula, you can compute explicitly what is the Bismuth connection on the Lie algebra. And so if you have the Bismuth connection, you can compute the curvature, right? It was the first formula we saw today. Here. Okay, here. If you have the Bismuth connection, you can compute the curvature. Okay. And so in particular, the only non-trivial components of RB, so for the Bismuth curvature, are this. RB of E1, E6, E1 is equal to E6, and RB of E1, E6, E6 is equal to minus E1, together with all the symmetries, okay, together with the symmetries. Okay, so for instance, how you do that? For instance, if you compute the Bismuth connection of E1, E6, E1, this is by definition nabla E1, nabla E6, E1, minus nabla E6, nabla E1, E1, minus nabla, the bracket of E1, E6, E1. But then nabla E6, E1, if you look here, is 0. Same nabla E1, E1 is 0. So we are left with minus nabla with the bracket of E1, E6, which should be, let's see, the bracket of E1, E6 is minus E2. Okay, is minus E2. Okay, so we have a plus here, nabla E2, E1, and nabla E2, E1 is E6. And so on, okay? So you can compute the curvature for the Bismuth connection in this way. And so let's check, for instance, the Bianchi identity, okay? So if we can compute RB of E1, E6, E1, so the Bianchi identity means that we have a cyclic sum. So RB of E6, E1, E1 plus RB of E1, E1, E6. This is symmetric, so this is 0 clearly. But then RB of E1, E6, E1 is E6. And again, because of the symmetry here, this is minus E6. And so we get 0. And so on. Okay, you can do, I mean, there are very few non-trivial terms here in the curvature, okay? So it's very easy to check that we have the first Bianchi identity. And so G, so let's say nabla B satisfies the first Bianchi identity. So first Bianchi, let's say. And similarly, if you want to check the other condition and for the type condition, you can check, for instance, RB of JE1, JE6, E1, and you want to be sure that you can get rid of these 2J. Okay, because the second condition is a J invariance condition. So this is RB of J of E1 is E6, and J of E6 is minus E1. And so for the symmetries, this is RB of E1 E6, E1. So you see, you can get rid of this J. So check, this is good. And so on for the other conditions, okay? For all the other elements in the basis. So nabla B also satisfies the type condition. So G is Bismuth Kähler-like. And if you want, as an exercise, you can check that G is actually SKT. It's an SKT matrix. Why am I leaving this as an exercise? Because we will see the relation between Bismuth Kähler-like and SKT matrix, okay? So it will not be really important to do the computation right now, okay? But you can check this as an exercise. Okay, so what is the conjecture? What was the conjecture related to Bismuth Kähler-like matrix? Because we said that when the Chern connection is Kähler-like, the metric is balanced. when the other Goduchon connections are Kähler-like, the metric is Kähler. So what if, when the metric is bismuth Kähler-like? What happens? So Angela, Otal, Ugarte, Villacampa conjectured that nabla B, being bismuth Kähler-like, implies that the metric G is SKT. Okay, so that was their conjecture. In fact, in this example, the metric turns out to be SKT. And this conjecture was, of course, supported by many other examples. So first of all, the first remark that I haven't done yet, so, but maybe you already thought about this, that if nabla B is flat, so means that the curvature of the bismuth connection is 0, then of course it is Kähler-like. I mean, all the symmetries for the curvature are trivially satisfied. So if nabla B is flat, then of course nabla B is Kähler-like. Okay, obviously. And in fact, Wang, Yang, Zhang studied bismuth flat matrix. So if nabla B is flat and M is compact, so I'm not assuming compactness today, okay? So in general. So, but when M is compact and the bismuth connection is flat, then Wang, Yang, Zhang proved that M admits as finite unbranched cover a local Samuelson space. Given by the product of a compact semi-simple Lie group and a torus. So let's say compact bismuth flat manifolds, Hermitian manifolds are kind of known, okay? We have that they have this special structure, but moreover, when nabla B is flat, okay, so the curvature of the bismuth connection is 0, then the metric G is SKT. Okay, and this was proven again by Angela, Otal, Ugarte, Villacampa. Okay, so in particular, so this is confirming their conjecture, right? Because bismuth flat matrix are in particular bismuth Kähler-like, and so they proved that the metric has to be SKT. And moreover, actually, they confirmed this conjecture. So again, Angela, Otal, Ugarte, Villacampa confirmed the conjecture on 6-dimensional compact submanifolds with holomorphically trivial canonical bundle. Okay, so they had some evidences for this to be true, okay? The fact that bismuth Kähler-like implies SKT. So with Arnafino, we tried to study the relations that we have between SKT matrix and the first Bianchi identity, right? Because, so let me show you again this formula. Because in general, we said the bismuth connection doesn't satisfy the Bianchi identity, but somehow the Bianchi identity is related to the vanishing of the torsion of the bismuth, the closure of the torsion, the differential of the torsion of the bismuth connection, which means when this is 0 means SKT, right? And then we have this other condition Okay, when this is 0, this term is vanishing, and somehow one would like to have the first Bianchi identity. Okay, so it seems that the first Bianchi identity is related to SKT matrix and parallelism for the torsion. So here's what we first proved. So first, we proved that if M is a complex manifold with an Hermitian metric G, first of all, if G is SKT and nabla B satisfies the first Bianchi identity, so let me say first B for the first Bianchi identity, okay? So then we prove that the torsion has to be parallel. On the other side, if we assume that the torsion is parallel, then we prove that G is SKT if and only if the bismuth connection satisfies the first Bianchi identity. So you see that how these three conditions are linked together, right? So on one side, if you assume SKT and first Bianchi, then the torsion is parallel. It's not a real vice versa, but if the torsion is parallel, then SKT and first Bianchi are equivalent. Okay, and the proof is based on some general formulas that relate, of course, all these objects. Okay, the curvature, parallelism of the torsion, and the fact that the torsion is closed, so the metric is SKT. So in particular, you see that first of all, as a corollary, so first corollary, what we have as a first corollary, we have that. So assume that we have MJG Hermitian, so an Hermitian manifold. If nabla B satisfies first Bianchi, then also we have that the torsion is parallel if and only if the metric is SKT. So this is SKT. It's the first corollary, okay? Assume that you have first Bianchi identity. Then, first side, assume that you have that the torsion is parallel. Then by 2, you have first Bianchi, torsion is parallel, so the metric is SKT. On the other side, assume that you have the first Bianchi identity and the metric is SKT, then you are here. If you have SKT and first Bianchi identity, the torsion is parallel, okay? So in particular, of course, as a second corollary, what we have that if G is Bismuth-Kähler-like, in the same hypothesis, okay, we have an Hermitian manifold. So if G is Bismuth-Kähler-like, in particular, it does satisfy the first Bianchi identity, is one of the two conditions of the definition of Bismuth-Kähler-like. So then nabla B TB is 0 if and only if G is SKT. Okay. Right. So, but in fact, we are not proving here that Bismuth-Kähler-like implies SKT. We are proving that if we have Bismuth-Kähler-like, SKT is equivalent to having parallel torsion. But in fact, the conjecture of Angella, Otalugart, Villacampa was proved by Zhao and Zhang in this theorem. So Zhao Zhang actually, so 2023, I think it was published this year. So if you have JG Hermitian, manifold, not necessarily compact, then nabla B is Kähler-like. If and only if the torsion of the bismuth connection is parallel with respect to the bismuth connection, and plus the metric is SKT. So in fact, they gave a characterization. So they proved not just that the bismuth Kähler-like condition implies that the metric has to be SKT, but in fact implies something stronger. The metric is SKT and the torsion is parallel. But also that, and this is kind of, I mean, it's very interesting, we have the opposite. So when the metric is SKT and the torsion is parallel, then the bismuth connection is Kähler-like. And so, but the proof is very different. I mean, the strategy is very different from the strategy we used with Annafino. We didn't, I mean, we use a coordinate-free approach. But on the other side, Zhao and Zhang used a coordinate approach, okay? We use here some very general formulas, but we consider just the first Bianchi identity. We didn't consider the whole bismuth Kähler-like condition, okay? We didn't use in this previous theorem the second conditions of being bismuth Kähler-like. In these results, there's no type condition, okay? Okay, but so I would like also to mention that in fact, in dimension 2, these metrics are well known. So these bismuth Kähler-like metrics are well known. So let me recall the following definition that every one of you know, because in this school, I mean, in this summer school, there was a course fully dedicated on this kind of metrics that are locally conformal Kähler metrics and Weismann metrics. So let me recall this definition. So let Mj be a complex manifold. So an Hermitian metric omega on M is called Weismann if, first of all, it is locally conformally Kähler. Which means that the differential of omega is a multiple of omega. So I will not call this form theta. So let me, and you will understand why. So let me call this alpha. So the omega is equal to alpha wedge omega for some D closed 1 for alpha. And the second condition for being Weismann is that alpha is not just D closed, but in fact is parallel with respect to the Levi-Civita connection, okay? So these are Weismann manifolds metrics. They are locally conformally Kähler, and this alpha is parallel with respect to the Levi-Civita connection. So just a remark about, let's say, the convention and the notation of what is the Lie form of a metric. Because sometimes this alpha, especially when you work with the locally conformally Kähler metrics, people tend to call this alpha the Lie form. But in the first lecture, I defined the Lie form in a different way. So I want to make this a little bit more clear. Otherwise, it can be a bit confusing. So notice that if d omega is equal to alpha wedge omega, then if you compute d omega n minus 1, this is d of omega wedge omega, etc., right? So it's just n minus 1 omega n minus 2 wedge d omega, right? Because you are applying the omega to the wedge product of omega n minus 1 times. Okay, so in the end, omega is a 2 form, so you get exactly this, right? You apply the Leibniz rule. But then the omega is just alpha wedge omega, right? And so this is n minus 1 alpha wedge omega n minus 1. Okay, so what do we have here? We have d omega n minus 1 equal to n minus 1 alpha wedge omega n minus 1. And then in the first lecture, I called this form theta wedge omega n minus 1. This was the Lie form of the matrix for me. Okay, so alpha and theta differ just for this n minus 1 multiple, right? So in our notation, let's say theta is equal to n minus 1 of alpha. And I called theta the Lie form, not alpha. But sometimes people call alpha the Lie form. The only important thing is, just not to be confused on what is your definition of Lie form. So in particular, for our notations, for us, alpha is 1 over n minus 1 theta. So this is 1 over n minus 1 of j d star omega, according to what we saw in the first lecture. So this is minus 1 over n minus 1 d star omega composed with j, okay? So this is, let's say, the alpha that appears in the definition of locally conformally Kähler matrix, okay? All right, but of course, if n is equal to alpha equals theta, okay? So for surfaces, alpha and theta are the same, okay? And in fact, so remark, so if n is equal to alpha equals theta, and moreover, one can show that the torsion of the bismuth connection is minus star of theta, where star is the Hodge star operator, okay? And it is kind of easy to see because the torsion of the bismuth connection, so this is because the torsion of the bismuth connection is dc of omega, so minus j minus 1 dj of omega. So this is minus j minus 1 d omega, because j of omega is equal to omega. And so this is minus j of d omega, okay? Sorry, j of d omega, j squared to minus the identity over 3 forms. And also on the other side, if we compute minus star of theta, this is minus star j d star of omega. So this star is minus star d star. So this is, so the minus cancels. So we have star j star d star of omega. But we are in dimension 2. So star of omega equals omega. And also, this is true in general, star and j commute because j is compatible with the matrix. So we have star square j d omega. So this is minus j d omega. Okay, so you see the torsion of the bismuth connection is equal to minus star theta. Okay. And also, okay, also, well, we do not need this. Okay, so let me just say the following fact. So why am I saying this? What we have on in dimension 2, okay? So I said that in dimension 2, Bismuth-Kähler-like matrix are well known. And in fact, they coincide with Weismann matrix. So first of all, let me recall this result that we proved. So suppose that we have 2j g omega, so on Hermitian surface. Okay, so n equal to. First of all, we proved that, so then G is Weismann. So on a surface, we have that G is Weismann if and only if the metric G is SKT. So SKT in this case equals Goduchon metric, okay? Because we are in dimension 2, Goduchon matrix were matrix such that DDC omega n minus 1 is equal to 0. But if n is equal to, a Gaussian matrix coincide with SKT matrix. Okay, so in particular, it is a general fact that every Weismann matrix is Gaussian. But also we have an additional condition, so plus nabla B satisfies the first Bianchi identity. Okay, so on Hermitian surfaces, Weismann matrices are Gaussian matrix, so SKT matrix, if you want, that satisfies the first Bianchi identity for the bismuth connection. Moreover, again, for surfaces, what we proved is that if RB of JX, JY, ZW is equal to RB of X, Y, ZW for every X, Y, ZW vector fields. So if we have the type condition, okay, this type condition here, this J invariance in the first two entries, then the metric G is locally conformally Kähler. So in particular, if a metric is Kähler-like, it is locally conformally Kähler because it satisfies this condition, okay? But in fact, so it is sufficient to have for Hermitian surfaces locally conformally Kähler matrix if you assume that. So it is sufficient to assume that the bismuth connection satisfies this this type condition. Okay. So in fact, Zhang and Zhang in the end proved that if you have an Hermitian surface, MJG omega Hermitian surface, then nabla B is Kähler-like if and only if G is Weismann. Okay, so on Hermitian surfaces, bismuth Kähler-like matrix are Weismann, coincide exactly with Weismann matrix. Okay, so somehow this bismuth Kähler-like condition, gives in dimension 2 reduces to having just Weismann matrix. Okay, it's not, let's say, it's not a new definition of a new class of matrix for surfaces. Just a remark that compact Weismann surfaces are classified. Okay, just so you know, they are classified by Belgun. Okay, so we know exactly which compact complex surfaces admit Weismann matrix. So we know exactly which compact complex surfaces admit bismuth Kähler-like matrix. But I think it is kind of interesting to conclude by saying that in higher dimension, this is false. Bismuth Kähler-like matrix do not coincide with Weismann matrix. But in fact, the general result is much stronger. So because in fact, in higher dimension, the situation, okay, so let me say this, the situation is very different. So we have this theorem due to Angel and Ottoman this year. It appeared on arXiv this year. So if you have M, a compact Weismann manifold of complex dimension n bigger or equal than 3, then, let M be a compact Weismann manifold of complex dimension n bigger or equal than 3, M cannot admit any SKT metric. Okay, so in particular, it cannot admit any bismuth Kähler-like metric. So you see somehow, so this result is saying that if you have a compact complex manifold, you cannot have both a Weismann metric and an SKT metric, but two different metrics. I'm not saying that the same metric can be, that is Weismann cannot be SKT. I'm saying that you cannot have two different metrics, one Weismann and one SKT. So this is the meaning of this result. So somehow is related to what we said in the second lecture. So because we said that we cannot have, I mean, it is conjectured that we cannot have both balanced matrix and SKT matrix, because, you know, it's kind of natural to ask if we can have on a complex manifold two different special Hermitian matrices. So in the balanced case, it is still open, the question. In the Weismann case, it was proven this year, okay? We cannot have on a compact complex manifold Weismann matrix and SKT matrix if we are in dimension equal or bigger than 3, okay? But on surfaces, Weismann matrix are trivially SKT because on surfaces, the SKT condition is the Goduchon condition, okay? And Weismann matrix are always Goduchon. And yeah, okay, I think I can stop here today. Of course, if you have any questions, feel free to ask.
Thank you very much. Any question? All right. Thanks to Nicoletta.